So now let us move to our second part of project, that will be dimension analysis of equation of change. So dimension analysis is very powerful tool used to simplify and non-dimensionalize the equation of motion, that will be Navier-Stokes equation, by introducing characteristic scales. This helps in identifying dominant forces, reducing complexity and revealing dimensionless numbers. For example, Reynolds number. Below are the key theories, which will be steps involved, and what we have to do is basically non-dimensionalize the equation of change and our Navier-Stokes equation. First point is non-dimensionalization of the continuity and Navier-Stokes equation. Governing equations will be continuity equation for basically incompressible flow and Navier-Stokes equation. uh, our continuity equation is del dot v equal to 0, and our Navier-Stokes equation is rho into dv by dt equal to minus del phi plus mu into del square v. Capital d by dt shows our different type of derivative which will be used in the Navier-Stokes equation. Now, characteristic scales involves introduce dimensionless variable using characteristic scales. Length will be L naught. For example, in different cases, L will be different. In tube, it will be diameter. For a plate, it will be its length. Velocity will be v naught, its average velocity obviously. Time equal to t naught, which will be L naught upon v naught. So this will be the dimensionless parameter for time. Coming on to the pressure, it will be phi naught, which is equal to rho into v naught square, uh, or phi naught equal to mu v naught by L naught. The first one, which is rho v naught square, is of inertial scaling, and the second one, which is mu v naught by L naught, is viscous scaling. Now our dimensionless variables will be, if we have dimensionless our length, then if suppose x is our length, then x bar equal to x upon L naught. L naught will our characteristic length. If suppose we have to dimensionless our variable y, so y cap will be y upon L naught. Similarly, z, x, y, z, any length variable, we have to divide it by L naught, then it will be dimensionless. For making our time to be dimensionless, we would divide it by either t naught, and for making our velocity dimensionless, we have to divide it by v naught, and for making our pressure dimensionless, we have to divide the pressure difference, that is phi minus phi naught. Phi naught will be any reference point or any initial pressure, divided by the difference by rho into v naught square, which will be on inertial scaling. Now, non-dimensionalized equation, our two equation, continuity equation and Navier-Stokes equation will be like continuity equation will be del bar dot v bar equal to 0. Our del is also dimensionless and our v dot also dimensionless. Now coming to the Navier-Stokes equation, d by dt bar of v bar equal to minus del bar of phi bar plus 1 by Reynolds number of phi del bar square into v bar. So basically we have to apply bar and we have to make every single quantity available in the equation to be dimensionless. And here Reynolds number is our basic rho VL by mu. Now further we will be discussing interpretation of dimensionless numbers.
Now we will see interpretation of dimensionless numbers. Number one, Reynolds number, which is inertial forces upon viscous forces. Inertial forces are is rho v naught L naught and viscous forces mu. So Reynolds number is equal to rho v naught L naught by mu. So we will see first case when Reynolds number less than 1, the viscous forces dominate, which means creeping flow, that is laminar flow. Second, Reynolds number greater than 1, inertial forces dominate, which means turbulent flow. Others numbers, if additional forces are present, there are two additional numbers. We will assume number one, Prode number Fr, which is denoted by Fr. For gravity effects, it only works. And number second, Weber number, which is symbolized by We, which is used for surface tension effects. We will see number three case, which is special case of the equation of change, in which we see first part creeping flow when Reynolds number is less than 1. Creeping flow means laminar flow. Now viscous forces dominate and inertial terms are negligible, which means equation becomes 0 is equal to minus del phi plus mu del square v, which is used for slow flows, that is microfluidics and stoke flow around the sphere. Number two, Euler's equation in viscid flow, which when Reynolds number greater than 1. Viscous forces are negligible in this case. Equation becomes rho dv by dt is equal to minus del phi, which is this equation is used for high speed flow, that is aerodynamics. Number three, non accelerating flow, which is for steady state, no time dependence. The equation becomes rho in bracket v into v dot del into v is equal to minus del phi plus mu del square v. Now we will see practical applications.
Some of the practical applications for this dimensional analysis is scale up and scale down of system, ensuring dynamic similarity between model and prototypes. Second application is identifying dominant forces, determine whether the inertia viscosity of gravity dominates or not. Third application is simplifying equation, reduces complexity by eliminating negligible terms. Uh, Now coming on to the summary of these key equations, which will our be studied in our dimension analysis. Full Navier-Stokes equation is there. The condition will be generalized case, and creeping flow, the dv by dt term will be zero. Rest will not be changed. The condition for the creeping flow is Reynolds number is less than 1. Now Euler's equation, in which we have Reynolds number is very greater than 1, called inviscid flow. In that we have dv by dt term. Also we have del phi term. The term which will be not there and neglected is mu into del square v term. Now, coming on to the non-dimensionalized equation, we'll have our bar equation like we discussed earlier. Every term like dv bar by dt bar equal to minus del bar phi bar plus 1 bar Reynolds number del phi del del bar square into v bar. All these are scaled variables, like these all are dimensionless, and whole equation is our dimensionless. Now all these things are related to our dimensionless our variables. Now coming on to the main part of the dimensionless analysis.
Now we will see dimensional analysis of equation of change. So we are going to see dimensional analysis of equation of change. So first, first we will see, there is a one equation, a del dot v is equal to 0. So we get the equation of change, which is rho d by dt dot v is equal to minus del p plus mu del square v. So this earlier told equation is of equation of change. In this, rho denotes density, v denotes velocity, and p, which is capital P, which is characteristic modified pressure, mu is viscosity. So we will see about the what are the scale factors. So first we will see L naught, which is characteristic length, which is for tube diameter. And now second one we will see characteristic velocity, which means average flow velocity. Now we will see characteristic modified pressure. So we will assume p naught is the final characteristic modified pressure. So we will say p naught is equal to p naught plus rho g h naught. So it is the modified pressure at the tube exit. So now we will see some dimensionless analysis of the equation of change. So first we will see for the x, y, z coordinate and for t also. So first for x cap is equal to x by L naught. So here we will divide by L naught to the coordinates for converting into dimensionless number. So for x coordinate in this case, which is divided by L naught. Similarly, for the y coordinate is y cap is equal to y by L naught. So for similarly z coordinate is equal to z by L naught. So for t coordinate in this case, t cap is equal to v naught into t by L naught. So similar as we have done for time, we will see for velocity. So v cap is equal to v by v naught. In this case we have divided velocity by v naught, so for converting into dimensionless number. So now modified pressure is equal to p p at final p minus p naught upon rho v naught square, or usually we can also say that p double cap is equal to p minus p naught mu v by v naught by L naught. So this we have get dimensional analysis. Now we will see del bar is equal to L naught L naught delta is equal to, we will see for del x, del y, del z. Here in place of del we have put dou by dou x up, and dou by dou y and dou by dou z for all three coordinates. So del cap is equal to L naught del is equal to del x into dou by dou x cap plus del y into dou y cap plus del z into dou by dou z cap. Now we are doing square of this equation, so it becomes del x becomes very small quantity, so it is negligible. So del cap square becomes del square upon del x x x cap square plus del square upon del y cap square plus del square upon del z cap square. So now equation become d by dt bar dt cap is equal to L naught upon V naught into d by dt. We have done multiply of L naught upon V naught to the d by dt, so to converting into dimensionless analysis. So now we have seen that equation rho by d by dt into v is equal to minus del p plus mu del square into v. So we are dividing mu by L naught V naught rho in this case. So the equation becomes, so now the equation becomes d by dt cap into v cap is equal to minus del cap p cap plus mu upon L naught V naught rho into del cap square v cap. So in this case we are also multiplying in front of minus del cap of mu upon L naught V naught rho. So now equation becomes, the final equation by manipulating the equation we got is this equation we are getting. So we will highlight. So this equation we are getting, which is dou by d cap into v cap is equal to minus mu upon L naught V naught rho del cap p double cap plus mu upon L naught V naught rho into del cap square into v cap. So we have seen, so now in this case Reynolds number is equal to Reynolds number is equal to L naught V naught rho by mu. So now further we will see two cases we are going to see when when Reynolds number tending to infinity, the equation we have seen earlier, which is d by dt cap into v cap is equal to minus del cap p cap plus mu upon L naught V naught rho uh, del cap square v cap. When Reynolds number tending to infinity, the equation becomes d by dt cap into v cap is equal to minus del cap p cap. So the equation this becomes infinity. So it eliminates. The final equation we gives when r tending to infinity is d by dt cap into v cap is equal to minus del cap p cap. This is known as Euler equation of change. And we will see second case when Reynolds number is less than 1. For this case we are when we are putting Reynolds number less than 1, the equation we get is equal to d by dt cap into v cap is equal to 0, and this equation is known as creeping flow equation. So we have seen two equations. When Reynolds number tending to infinity, that equation is known as Euler equation of change, and when Reynolds number less than 1, that equation is called creeping flow equation. Now we will see some basic questions on dimensionless analysis. First question is, why is Reynolds number so fundamental in fluid mechanics?
Uh, that's very basic question actually. The Reynolds number is predicting for laminar or turbulent flow in fluid mechanics. So our whole problem is based on laminar turbulent condition. That's why it is very fundamental in fluid mechanics also. So my second question to you is, how would you dimensionalize heat transfer equations?
In terms of heat transfer, we will introduce two numbers which usually use number one Peclet number and number two Prandtl numbers for convection versus conduction. Question number three: what's the flaw in ignoring Froude number in ship hull design?
So wave drag scales with Froude number mismatched Froude number leads to incorrect wave resistance prediction. That's why we'll be ignoring Froude number in ship hull design. My next question to you is, can dimensional analysis predict chaotic systems?
Mm, answer of this question is, we will see partially strange attractors. Example, a Lorentz system requires nonlinear dynamics. So, so the strange attractors require nonlinear dynamics. Question number five: why does Reynolds number appear in both pipe flow and aircraft design?
Uh, the null number is appearing both pipe flow and aircraft design because in pipe we compare inertia versus viscosity. Whether in aircraft design we should be handling our pressure and pressure velocity theorems in the wings for designing wings of airplanes. So velocity will be high, therefore pressure will be low in the lower ranges on the wings of the airplane, so that the pressure difference cause force, and this force will be used for uplifting the airplane. That's why Reynolds number is very plays very essential role in both pipe flow and aircraft design. Now, my next question to you is, how does Mach number, which will be denoted as MA, change compressible flows?
Uh, in this case, Mach number which is greater than zero point 0.3 introduces density variation requiring Euler's compressible forms. So Mach number which should be greater than zero point 0.3, which introduces density variations. Question number 7: what's an example of field dynamics similarity?
An example of field dynamic similarity is, in 1919 Tacoma Narrows Bridge unscaled wind effect caused resonance collapse. So, like, we have to take care of every small things while creating the social or any public resources. My next question to you is, how do you scale up a lab reactor to industrial size?
uh, Match Reynolds number, Dan Kohler for chemical kinetics and power by volume ratios. Uh, uh, by this, we will scale up lab reactor to industrial size.
Okay.
So, question number 9 is, why is we important in inkjet printing?
Uh, V means basically Weber number. It controls droplet breakup versus surface tension. When Weber number is greater than 1, it shows splattering. Now my next question is, like, very broad point of view, can AI replace dimension analysis?
So basically, the answer of this question is no. AI lacks physical i- intuition. DA provides foundational scaling laws. Hence, AI can't replace dimensionless analysis.